And now I would like to invite our next speaker. It's Professor Viktoria Aviyente. And Viktoria will tell us about computational study and design of donor-acceptor copolymers for organic photovoltaics.
Yeah. Okay, hello everyone. So our work is on modeling donor-acceptor copolymers for organic photovoltaic materials. So this is a computational study, and I will try to give you some details on how we did the calculations and what is that we learn at the end. So first of all, we did some benchmark calculations, and we have chosen some donor-acceptor polymers, and we have introduced thiophene in between to see the effect of thiophene linkage. And we started by doing our calculations in the monomer level, then dimers, trimers, and we have ended up seeing that the tetramer, in fact, gives us the best agreement with experiment. So these are some of our benchmark calculations, and we see that the experimental band gap is quite well reproduced with the methodology used. By the way, we have used several DFT functionals such as WB97, PBO0, MO6, and apparently B3RYP, in spite of neglecting the dispersion effects, seems to reproduce quite well the band gap. So now, regarding the band gap, there are many approaches in the literature, and we try to figure out most of them. So first of all, we have considered the neutral singlet ground state. So this is just the neutral singlet ground state. And we also considered for other alternatives. What does that mean? We have, instead of looking at the singlet as it is, we try to look at the cation, at the anion. So what for, apparently in some cases, those reproduce better the energetic levels of the HOMO and the LUMO. That's why we try to do that. And we also look at the neutral triplet state, and finally, we have performed TD-DFT in order to see the band gap. So all of these calculations ended up in a way to give us the best agreement with the experiment with TD-DFT rather than the others. And the neutral single state gave us good agreement for the HOMO, and the neutral triplet state gave us good agreement for the LUMO. So with this, we went a step ahead, and we tried to see what is the distortion energy. So we don't need all these numbers. I will just tell you briefly what we define as distortion energy and what is that used for. It is used to tell us how good our polymeric chain is in terms of delocalization of electrons. So when you pick up the tetramer, there are many torsional angles, and there is, of course, the possibility of torsion and of the distortion. So as we know from organic chemistry, the less distortion the molecule has, the better is the delocalization of electrons. So we wanted to see, in fact, how good is the distortion in this long chain polymers when you have the bi-thiophene ring in between, or when we don't have it. And apparently it turned out that we have the least distortion when we have the thiophene in between. So that was as expected. And over there we calculated the reorganization energies, and the purpose for it was to try to correlate the reorganization energy with the band gap and with the electron transfer. Apparently here again the reorganization energy is smaller for donor thiophene acceptor thiophene species. So in other words, when you introduce thiophene in between, the reorganization energy is smaller. So this will lead us to choose this copolymers better than the others. So there we see the three-dimensional structures of some of these copolymers. Just a brief one sentence to illustrate this figure. So when we introduce the bis thiophene rings in between, the better the delocalization of electrons. And finally, this is a slide which illustrates how we have chosen these copolymers. In other words, how we have suggested these copolymers as being potential copolymers. We have checked the band gaps, the low reorganization energy. Okay, so and from here we have compared the HOMO and the LUMO to the PCM HOMO and LUMO, and a 0.3 EV difference is an acceptable difference for this band gap. And we wanted LUMO energy to be higher than 3.8 and HOMO energy to be between these two numbers. This is the air, the oxidation by air. So we have tried to obey this criteria for the polymers chosen. And here we have highlighted the copolymers which obey this criteria. So overall, we have tried to suggest a method to do some predictions on the usage of these copolymers as donor-acceptor units. So this is the first part of the talk. The second part of the talk will be a short one, but I just want you to, very, very short one actually, just to tell you how we approach the degradation process. So this is another study which was carried out before this one. This is related to boron-containing polymers. These are widely used. As you may know, boron is an acceptor, and it has very good properties when it is, when it is with phenyl rings. When it is, the figure is not as good as it used to be anyway. So when it is, so here is boron, and you have the phenyl rings around it. So over there, this is a benchmark. I skipped the benchmarks, but I just want to tell you that we did benchmarks which gave us excellent results with literature. Over there, the main idea, this is the main point, we have found out that one of these polymers had a very high cross-section. So just telling us that it could be used for 2-photon absorption. So this was a nice finding, and we want to see how good or how the degradation process occurs for this polymer. Is it comparable to the others or different than the others, and why does this cross-section is as high as that one? So this is what we plan to do in the very near future. We have started already. We try to model the degradation mechanism of these polymers, and we want to see why the triphenyl copolymer is, in fact, has a very high cross-section, and we want to see whether the degradation process is different than the others or so. So with that, I want you to share a view of Boğaziçi University in Istanbul. It was founded as Robert College in the 19th century, and this is still there today, and it's called Boğaziçi University, and this is where the chemistry department is. This is a group picture, and thank you all for your attendance, and thank you for the organization. By the way, I have a poster 9. I'll be around, and if you are interested in modeling, I'll be happy to talk with you.
Thank you very much, Victoria.
Thank you.